Good afternoon, everyone. So I'll be talking about irradiation and temperature aging of EPDM polymer, and I will specify my talk to the comparison between mechanical properties of industrial and neat EPDM material. This work is done through collaboration between SK Nuclear Institute, UCL University and Laborelec, and all the companies and institutes are coming from Belgium. So this project is dedicated to the study of cables that are in use in nuclear power plants. So far, there was no clear monitoring program established, and after years and years of operation, of course, these cables age, and it is important to know and to predict their state with respect to the future long-term operation. This study especially is focused to the outer insulation layer of the cables that is made out of rubbery polymers. This outer layer of the cable is the most exposed one to the environmental degradation factors, among which have elevated temperature and gamma irradiation. So we need some additional analysis and in order to support the monitoring and validation for the long-term operation of the entire cable. Approach that we are going to use is to study mechanical and physicochemical properties of accelerated aged polymers and to support these studies by modeling. With respect to the material choice, we have samples that are extracted from the cables that are in use in nuclear power plant, and the main polymer component is EPDM polymer. This is the copolymer between polyethylene and polypropylene. But other than EPDM, in these samples we also have some other polymers like EVA and some other additives like aluminium hydroxide that is a fire retardant. Because of this, we decided to perform the same experiments on neat polymer that is commercially named NORDEL and engaged, and today I will present my results on NORDEL neat EPDM. So we performed also accelerated aging, and we variated temperatures, dose rate, which is irradiation flux, and also doses, which means the irradiation flux multiplied by the time that sample was under the irradiation conditions. We especially focused to have the variation of dose rates because we want to study so-called dose rate effect that I will be explained to you a bit later. So before I start to talk about the results, I would like to mention to you the main mechanisms degradation mechanisms that affect polymer. So this polymer network microstructure is responsible for elasticity properties. And there are few mechanisms like creation of new bonds known as cross-linking, breaking of existing bonds known as chain scission, and reaction with oxygen, so the oxidation process, that change and affect this polymer microstructure. They are all happening in the same time during the degradation process, and dose rate affect these three processes. Because of that, it is important to study it. And now, in practice, we see the dose rate effect as difference in mechanical properties for the polymers that are aged up to the same dose. So, for example, if we check the ultimate tensile stress, we can observe that it increases and decreases. It increases if we have cross-linking, so creation of new bonds as dominant mechanism, and it decreases if we have chain scission, breaking of bonds, as dominant mechanism. And we can observe this maximum, which is the crossover from cross-linking to chain scission dominance. So how do we observe dose rate effect on ultimate tensile stress? We observe it as a shift of this crossover as a function of the dose. We can also see that this shift exists for the moderate temperatures, but it is even stronger at high temperatures. And also we can observe that if we have the same dose rate but different temperatures, again we can observe the shift of crossover in a way that increase of temperature will shift it toward the lower doses. Now, with respect to the elongation and break data, this dose rate effect is a bit less obvious because both cross-linking and chain scission induce decrease of elongation and break. But still, for some extreme conditions like very low dose rate, especially at high temperatures, we can observe that the decrease of elongation and break is much faster than for the high dose rate. So this is a clear indication of dose rate effect. Elongation and break data are also used in engineering approaches in order to establish end-life criteria. So we plot relative elongation as aging time versus aging time, and we use existing models in order to predict the behavior of relative elongation. So we used here Menlo and Duncan model that gives the aging process as sum of thermal and irradiation processes, which are both given in form of activation energy equations. And what is the most interesting is that we could fit all of our elongation and break data by varying only one parameter, which is this reaction rate from the irradiation part. Also, this constant is found to be very dose rate dependent, and moreover, this dose rate dependence is found to follow the square root. And this is important because in previous investigation it is found that this square root dependence might originate from the oxidation effect. Second very interesting test is indenture modulus, that is important because it is a non-destructive test. So indenture modulus increases with dose, so it increases with aging, and again we can observe dose rate effect. So we can observe a faster increase for low dose rates in comparison to the high dose rates. Moreover, we observe a great correlation between indenture modulus and elongation and break data. And now, of course, the question raises, why do we have such a good correlation? And you will see later on that this question is actually very related to the origin of dose rate effect itself. So now I'm going to present you the mechanism that can explain all of our data, and I would just like to mention that it is also supported by our chemical analysis, which are not presented here today. So, during the aging process we have oxidation. It can be heterogeneous and homogeneous. Heterogeneous oxidation is very important for the high dose rates because we have fast oxidation. It is only strong near the surface of the sample. But if we have low dose rate, we have more time in order to have the same dose, and oxygen has time to diffuse into the sample, and oxidation is more homogeneous. Also, increase of temperature will enhance the diffusion of oxygen, so it will enhance the homogeneous oxidation. What does this mean for our mechanical properties? So, if we have thin oxide layer, we will have prevailing of cross-linking, and we will have increase in ultimate tensile stress. If we have a thicker oxide layer, we will have promotion of chain scission mechanism, and we will have dominance of chain scission mechanisms. And for the elongation and break, this means that oxide thickness is what governs the decrease of elongation and break. Also, the same oxide thickness governs the increase of indenture modulus, and that's why we see a great correlation between these two mechanical properties. So, in order to explain the modeling, elongation and break versus time can be modeled with only single parameter because both temperature and dose rate affect the oxide thickness. So the growth of the oxide is a time dependence. And moreover, we found that for industrial EPDM polymer, the oxidation seems to be the main degradation process. Now further, we will compare our data with the data for the neat polymer. First of all, when we did the tensile test, we noticed the first main difference in the stress-strain curve. So first of all, we can see that neat polymer elongates almost up to 1000%, while our industrial polymer goes only up to 130. So it is expected because our industrial polymer has a lot of additives that will decrease the elongation properties. Second point is that we can observe yield point in the stress-strain curve. This yield point is observed because of crystallinity that is present in the neat polymer, and it is much reduced in the industrial polymer, again because industrial polymers has a lot of additives that prevent polymer crystallization. Also, in practice, we can see the consequence of this necking process after our tensile data. So you can observe existence of this necking or narrowing of neat polymer, but the same is not observed for the industrial polymer. So it recovers its shape fully after the extension. Moreover, we can observe that with aging, we have lost this yield point, and then for the high doses, neat polymers actually behaves like industrial. What is the origin of that? Probably destruction of this crystallinity part, but still it has to be proven with some additional chemical analysis. Further on, if we compare elongation and break versus dose data, we can first of all see that these open spots are for neat polymer and the dark spots are for the industrial polymer. So the elongation and break decreases much faster in neat polymer. And again, we can observe dose rate effect, and it is much stronger at high temperature. Second of all, if we compare ultimate tensile stress data, we can observe that this crossover point from cross-linking to chain scission process appears at lower doses in comparison with our industrial polymer. Again, dose rate effect is still present in neat polymer. So this brings us to a conclusion that our neat polymer is much less chemically stable for the same aging conditions, and this is expected because industrial polymers also has some antioxidants in its compound, and also it has a lot of additives that prevent diffusion of oxygen. Further on, we did the same model. We applied the same model in order to study elongation and break data of neat polymer, and now we don't observe anymore this square root dependence. Now the dependence of this constant versus dose rate is more linear. So now this brings us to a question: is oxidation still the main degradation mechanism in neat polymer? Again, in order to further analyze this, we need to do some additional chemical testings. So in order to conclude, finally, elongation and break and ultimate tensile stress are both found to be very dose dependent. In ultimate tensile stress, we observe a dose rate effect, but it is a bit less evident for the elongation and break data, and this is because cross-linking and chain scission have different influence of these values. NORDEL or neat polymer is found to be less chemically stable, which is expected, and also elongation and break experiments can be modeled with one parameter. This parameter has a square root dependence for EPDM, so we consider that oxidation is the main degradation process, but the same was not found for the neat EPDM, so we still need to do some additional investigation in order to try to evaluate the main degradation mechanism for the neat polymers. So thank you for your attention.